This is the Algebra 2 lesson for section 14.3, and this is going to be day 1, and it's about right triangles and trigonometric ratios. And remember, the trigonometric ratios we learn in geometry as SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And often we have to use those alongside or with the Pythagorean theorem in order to get what we need. And we're just going to talk specifically about right triangle trig ratios. So objective, to find lengths of sides in a right triangle, and then to find measures of angles in a right triangle. And we use a combination, if we have to, of, again, the Pythagorean theorem and or SOHCAHTOA to figure out what it is that we need. So there's definitely a connection between the trigonometric functions and the right triangle trigonometric ratios that you studied in geometry. So we're going to put a couple of things together here because, like it says, we're going to look at this a little more in depth with trigonometric functions. And all the things that you know about SOHCAHTOA absolutely are going to hold. In fact, they're going to lead us to some other formulas and things that we can use. So our essential understanding is if you restrict the domain of the trigonometric functions to angle measures between 0 and 90 degrees, the function values are the trigonometric ratios associated with the acute angles of a right triangle. Because of course, if we go all the way to 90 degrees, we only have 90 degrees left for the other two angles, which would, by logic, make each one of those less than 90 degrees. And now at the bottom here it says dilate the unit circle by the factor r, and the terminal side of an angle theta will intersect the circle of radius r in the point xy, and we can use these little formulas to find it. R times the cosine of x and r times the sine of theta. And at first, I'm sure you're looking at this thinking, wow, I never learned that in geometry. And you would be surprised to know that, yes, in fact, you did. But it's just a little different way of thinking about it. So I look at these as if they're a formula that needs to be solved. And I start thinking, okay, well, we all know that cosine was adjacent over hypotenuse. So I think I'm going to get cosine by itself. And that would tell me that since cosine is adjacent over hypotenuse, that the adjacent side is the x-coordinate that I have, and then my hypotenuse is whatever the radius is of that circle, r. And then for sine theta, if we divide both of these by the radius, we come to understand that y is going to be opposite and r is going to be our hypotenuse. So when you look at these as formulas that can be manipulated, a lot of different things will happen. And I want to show you the picture here so that you can put all that together with what we were just talking about. And what we have here is a unit circle, and you see that in the red right here. That is the unit circle, and notice the radius of that circle is a 1. And then what we want to do is we want to figure out, well, what happens to that if we are, drop my marker, dilating that. And that would give us the blue. Well, here's our theta right here, the angle in the corner. And so we're trying to figure out how could you get both your x and your y coordinates if you needed them. Well, if this is our angle, then we know r is going to be the hypotenuse, because here's our right angle, and the hypotenuse is always opposite the right angle. That's our definition from geometry. So if we need x, x is going to be adjacent to our angle theta, because adjacent means right next to. So if we were going to set something up with that, we would have to use adjacent and hypotenuse, which of course is cosine. So the cosine of theta would equal adjacent x over hypotenuse r. And like we saw just a minute ago, if we multiply both sides by r, x is really going to be r times the cosine of theta. Now, if we need y in the mix for some reason, that side is opposite angle theta. Remember, opposite as far away as you could possibly get from that angle in the triangle. And we would continue to use that radius. So we would have opposite and hypotenuse is the sine of theta. And again, you would multiply both sides by r. And you receive the little formula that we had. And in fact, it's right up here to figure out your x and your y values. So what we see here are formulas that you can use for a multitude of things that you need to find. And we're just going to touch the surface of this. So we go through and we see sine is y over r. And again, if you're not a memorizer, you don't have to be. You could draw the picture and you could do your SOHCAHTOA and go from there. Cosine theta is x over r. And then tangent theta is y over x, because y over x would be opposite over adjacent in our picture, and of course that's tangent. Now, what we have to remember is these are the primary trig functions. Primary trig functions are sine, cosine, and tangent. Our secondary trig functions are their reciprocals, and that's going to be for sine, the reciprocal is cosecant. For cosine, the reciprocal is secant, and then for tangent, the reciprocal is cotangent. And you notice all we have here to work with are reciprocals. They've just been flipped. That's the only difference. So what we have to get across to ourselves is y is important when we're looking for sine. So it's going to be y over r by looking at the picture that we have over there. Cosine, the x is going to be important. X over r. And then tangent, y over x. So what we need to be able to do is figure out what is x, what is y, and what's r. Now, this one says trigonometric values beyond the unit circle, and it says for a standard position angle determined by the point 8, -6, what are the values of the 6 trigonometric functions? So what you want to do is think of this graphically, that this is 8 units, and this is your -6, so that's 6 units. And we're not supposed to calculate any of this without knowing what r is. Well, r is the hypotenuse of that right triangle. So we can really just use a squared plus b squared equals c squared here. Or you might even remember that as a famous Pythagorean triple, and that's going to be 6, 8, 10. But let's just say you don't remember that. You continue to do the math. And we take the square root, and because this is the side length for a triangle, we of course ignore the plus or minus and just go with the positive for that one. So C would be 10, that distance that we have right there. So now I want to go through and figure out what does all this stand for. Well, 8 is my x value, and -6 is my y value, and I do want to have that negative piece in there. I don't need that in the Pythagorean theorem, because when you square something in the Pythagorean theorem, it becomes positive anyway. But I do need that for y. And then our r value is going to be 10. So we have all of that labeled and ready to go. And then all we have to do is find those angles. And we can use the formulas, or we can use the markings that we see over there from our triangle and say, all right, well, theta is actually outside this angle here, you know, and that's the piece that we're going to look for. But when we do sine and cosine and tangent, the sine of theta is created just by the coordinates alone. So the sine of theta is going to be -6/10. And that's because it is y over r. And then we would, of course, reduce that to -3/5. The cosine of theta is going to be x over r, which is 8/10, which is 4/5. Then the tangent of theta, determined by that ordered pair of 8, -6, is going to be y over x, or -6/8. So these are all the formulas from the previous page. And now, really easy to get cosecant of theta. secant of theta and cotangent of theta, because all we have to do is flip, take the reciprocal of sine, cosine, and tangent in that order. So negative 5/3 for cosecant, 5/4 for secant, and negative 4/3 for cotangent. So again, they are determined by that ordered pair. So as we look at this, things are set up very nicely. Now, we don't get a picture for the got it. And it says for a standard position angle determined by the point negative 512, what are the values of the 6 trigonometric functions? But I remember that all I really have to do is figure out what r is, and r is that radius, which is the hypotenuse. So I can put the negative 5 and the 12 in as the 2 legs of the right triangle, the 2 sides. And again, this one is a famous Pythagorean triple. It's 5, 12, 13, but if you don't know that, you can continue on with the math and get 169 and take the square root, and you will get that 13 in the end, because again, we simply ignore the negative of that because this is side lengths of a triangle. So the x value is obviously negative 5. That is in the x position. The y value is 12 because that's in the y position. And we just figured out what r was. R was 13. So you think sine of theta is y over r. Cosine of theta is x over r. And tangent of theta equals y over x. So negative 12/5. And then we need our 3 secondary trig functions, cosecant, secant, and cotangent. And just take the reciprocals in that order. So we're going to take sine, get the reciprocal of that, that's cosecant. And then we are going to take cosine and flip that one to get secant. And then tangent, flip that to get cotangent. And there they are. So you determine your x, your y, your r, and then you can just use the formulas, or you can use the picture and think about your SOHCAHTOA as you go through there. But when we're given coordinates, we really would like to just use those coordinate patterns that we have. The y over r, the x over r, and the y over x. In the first quadrant, the values of x, y, and r are positive. So keep in mind, this is a European model, therefore those quadrants go counterclockwise as you look at our Cartesian coordinate plane. Then, the values of the trigonometric functions are positive for an acute angle theta of a right triangle, So those are going to be positive values that we're looking for in the first quadrant. Now comes what you are very familiar with, and that is the SOHCAHTOA piece. So if theta is an acute angle of a right triangle, x is the length of the adjacent leg, and we're just going to use ADJ to stand for that. Y is the length of the opposite leg, OPP, and R is the length of the hypotenuse, HYP. Then the trig ratios are SOHCAHTOA. Sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent, better known as SOHCAHTOA. And then, of course, the reciprocals of those are our cosecant, secant, and cotangent, our secondary functions. So as we look at the triangle, the way that you really want to label these is in the order of opposite, hypotenuse, and adjacent, or hypotenuse, opposite, and adjacent. Why do it that way? Because the opposite is the side that has nothing to do with the angle. It's not touching it whatsoever. If you look at this side, it is not touching angle theta. And then the hypotenuse we will always know, because that, of course, is always going to be the side opposite the right angle, or if we can tell, some triangles are so small you can't tell which one is the longest side, but it will be the longest side. And then adjacent means right next to. So now there's no question that what we have left for adjacent is this side length down here, which is x. So again, it generally, find a way to do it. What I mean by that is, find a way that you're comfortable with. I always do opposite, hypotenuse, and then adjacent. You can do hypotenuse, opposite, and then adjacent, but follow that pattern and then you're less likely to make a mistake. When using right triangle trigonometry for real-world applications, be sure to set your calculator to degree mode. So when we are given degrees and we are working with degrees in the triangles, we have to make sure that our calculator is set to degree mode. So what we have to do now is, I'm going to go back to the calculator here and show you how to get that in degree mode. What we need to press is directly to the right of the second button. That's the mode button, the one in the red that you see right there. And now what we have to do is come down to where it says radians. Radians are another measurement that we use in place of degrees, and actually it is more accurate than degrees are, but we're not at that point yet. So we're going to go ahead and move Blinky until it's over the top of degrees, and Blinky is going nuts, and we're going to press enter. So that tells the calculator we want this in degree mode, and you can arrow down if you want to just to be sure, but you should see that black, the darkening over degrees right there. And now, if you hit second quit, everything that you work with will be in degrees until you change your batteries or you reset your memory. So you shouldn't have to do that several times as long as you don't have to reset your memory or change your batteries. So now, we want to use this information to figure out some missing measurements. And this one is about finding distance, and this is the large glass pyramid at the Louvre in Paris, and it has a square base. It says the angle formed by each face in the ground is 49.7 degrees. How high is the pyramid? Actually, they're not using the language here that they probably should, which is the angle of elevation. Because if you're on the ground and you're looking up, this 49.7 degrees is the angle of elevation. So now what I want to do is I want to use the fact that this is a square base and realize that if an entire side is 35 meters, that means, and I'm going to move this down where you can see it a little better, we can take half of that and use it to go right to the middle of that pyramid. So 35 divided by 2 would get you 17.5. And now they wanted us to figure out how high is the pyramid. So that's the x that we see here. To do that, we need to think about our labels. So I'm looking at this pyramid and I'm thinking, all right, this x here, that is opposite. Hypotenuse, I'm not going to use. I don't have any information over there that's helpful at all, but I'm definitely going to use this number that they gave me for adjacent. Notice I didn't even write down HYP because I don't want to be distracted by something that I don't have any information for. So then I think, all right, now I've got to come up with a trig function, SOHCAHTOA. What I need is one that just uses opposite and adjacent, because I need to find the opposite side and I've been given one of the adjacent sides. Well, that is tangent. So the tangent of that 49.7 degrees is going to equal x opposite over 17.5. And remember, the tangent of 49.7 degrees is a number. It is stored in your calculator. It's waiting for us, ready to use. So we are going to multiply both sides by 17.5. So we're going to be punching in 17.5 tangents of 49.7 degrees in order to figure out what that x value is. So let me see if I can get back to the calculator without too many issues here. All right, so we have this set in degree mode. Now I'm going to need 17.5, and you can punch in times or not. The calculator really could not possibly care less if you put that multiplication in there. It knows what it's supposed to do. and I'm just going to finish off those parentheses. So 17.5 tangent to 49.7 degrees, and that we will go tenths, so 20.6. So we have found the height of the Louvre to be approximately 20.6 meters. Like so. Again, a picture is incredibly helpful and important here. So if we are not given one, then we probably want to make one anyway, So the next piece says, what is each distance for the Louvre pyramid? And we want to figure out the pieces that they want here. So A says, from the center of a side of the base to the top along a lateral face. From the center of a side of the base to the top along a lateral face. All right, well, let's go back to the picture up here. So what they're really asking us for is right here. That's what we want. So I'm going to go ahead and make a sketch again of this triangle. And we had 17.5 right here, and they gave us 49.7 for that angle. And over here we said this was 20.6 meters, approximately. But you know what? We might have messed up. So some of you might say, well, let's just use the Pythagorean theorem, 17.5 squared plus 20.6 squared. But if we messed up on that 20.6, then we're already using bad math and we're doing more math with it, and it's going to be twice as bad. So instead, I'm going to stick with what they gave me. And that is, they gave me the adjacent side, and I need the hypotenuse. So maybe I'll have that be y this side. And I think about my SOHCAHTOA. And what I'm looking for is something that just uses, a trig function that just uses adjacent and hypotenuse, and that's going to be cosine. So the cosine of 49.7 degrees equals 17.5 over y. Now, something interesting has happened here, and that is that our variable is in the denominator. And we've talked about this before, that when you solve, you cannot leave your variable in the denominator. So first thing to do is multiply both sides by y, and then we'll see what's going on with this problem. Well, now I realize that it's y times the cosine of 49.7 degrees. So I am going to have to divide by the cosine of 49.7 degrees. Because again, that is just a number. It's in my calculator and it's ready to go. So I have to grab my calculator and punch in 17.5 divided by the cosine of 49.7 degrees. And let's see that magic calculator here. So calculator, we need 17.5 divided by the cosine of 49.7 degrees. And important this time to finish off, although it's important every time, but finish off those parentheses so the calculator knows, hey, there's no more math coming here. Just take 17.5 divided by the cosine of 49.7 degrees. And that will be 27.1 meters. All right, so far, so good. Now it says we want to figure this out from a corner of the base to the top. From a corner of the base to the top. All right, so let's think about where that's going to be. The corner of the base to the top. Well, now that is interesting. So we have to figure out how can we get everything that we need based on what we see here. And what we're going to know is this is definitely going to be a right angle right here in the corner. And then we think, okay, well, how could we get any of this information that we need here? Well, this is a square base. So if we're going to cut this way, we are going to create a couple of 45, 45, 90 triangles here. And if that happens, you can remember the relationship between the 45, 45, 90s, and that is they are always isosceles, and to get the hypotenuse, you multiply by the square root of 2. So we can work backwards here because we have the hypotenuse, it's 35, and we can divide that by the square root of 2, and that will get us the distance from the center of the pyramid out to that corner, and that will be a big help to us. So doing the math here, multiplying the numerator and the denominator by the square root of 2 will get us 35 square roots of 2 over 2. All right, so now let's see what we have. So far, we know this distance is going to be that 35 square roots of 2 over 2. Now, we might want to write that as 17.5 square roots of 2 since this is a real world problem. It'll be a little easier. If we just do that with a decimal, we're going to have our answer in decimals anyway. So now what do we know? Well, we know that this is 17.5 square roots of 2. And we know that this is 20.6. And this way, we could use the Pythagorean theorem because at this point, we don't have any choice. You know, we've used our 45, 45, 90. Things should be working out pretty good. So I'm going to go down here and make a sketch of what our triangle looks like for part B. Remember the very top up there, we said this was 20.6, and by using that 45, 45, 90 triangle, we have 17.5 square roots of 2 right here. And so what we would be looking for is our hypotenuse. So we would take 17.5 square roots of 2, square it, add that to our approximately 20.6 squared, and that will get us c squared. And when you punch all of this mess in over here, it's about 1036.86, and then you take the square root. And again, we're just going to ignore the negative here, and it's approximately 32.2 meters. So that would be what we need to do there. Now, if you don't remember the relationship between the 45, 45, 90, you can still figure out that 17.5 square roots of 2 by saying, okay, my two side lengths are x squared plus x squared has to equal our 35 square roots of 2 over 2 squared. Not going to be a lot of fun, but you can do it that way. You know, like a lot easier to remember that special relationship in a 45, 45, 90 triangle. Now, down at the bottom, oh, actually it's on the next page on this one. We have that in a right triangle, in the right triangle trigonometry, the value of 1 trigonometric ratio determines the values of all of the others. So we can use the fact that we know one of the trig functions to determine what the other ones are. So let's take a peek. It says in triangle ABC, AC is a right angle. All right, best in geometry to have a picture. And the sine of angle A, so we'll think of that as our theta, is 5 over 13. And I remember it's SOHCAHTOA. So this sine is telling me that the opposite side is a 5. That would be that side right there across from that A. And then my hypotenuse is a 13 right there. And then they ask us what are some trig ratios that we see over there. Well, the first thing I would do is say, well, I need this one. I need to know what that is. So I will just call this little b here because it's right across from capital B, and in right triangle trigonometry we tend to use those patterns of the uppercase for the vertex and then across from it is the lowercase for the side. So again, if you don't recognize this, you could always use the Pythagorean theorem, but this is that famous Pythagorean triple that we saw just a little while ago. B is 12. So either use the Pythagorean theorem or use what you know. And then it says what are the cosine of A. So I go up to A and I realize if I'm using A and I need cosine, cosine is adjacent over hypotenuse. So I need the adjacent side for A, which would be 12, and then I need the hypotenuse, which is 13. So the cosine of A is 12/13. Then we have the cotangent of A. Well, I'm just going to go ahead and find the tangent and then flip it. So the tangent of A is opposite over adjacent, and that will be 5/12. So the cotangent is going to be 12/5. And then they want the sine of B. So now I need to switch position here and think about B as my new angle. And the sine of B, sine is opposite over hypotenuse, will now be 12/13. And that, I believe, is a pretty good place to stop with this section. So when we start up again, I'll probably go through the got it 3 just to remind you about that, and then we'll finish up the rest of this section. The homework will use the concepts that I have just gone through. And there it is, section 14.3, day 1, on page 916, getting pretty far in the book back there. Numbers 7 through 17. 53, 56, and 63 to 65. So please complete that by next Tuesday, which will be Tuesday the 24th.